My name is Marco Seppi. I am a product manager for cable assemblies, and today I will guide you to face the topic of phase stable cables, cable assemblies for space applications. The topic I will talk about will not be extremely technical, but I will give a few hints about how we manage to work with polymers, extrusion processes, and technology in order to reach a high phase stability in different temperature conditions with our RF radio frequency cables. The environments in which we are working can be pretty demanding. We are working in variable temperatures, and we are working with high radiation, and therefore we have to consider the right material for the dielectric in our cables in order to achieve reliable and stable performances. But I will not go immediately into the topic. I would first like to give you a few words about HUBER+SUHNER, what we do, and how we can serve our customers for the space applications. HUBER+SUHNER is a component manufacturer for interconnectivity solutions. We are very strong in the industry segment. We also work in different segments, but here you have an overview of what we are doing in the industry segments in different markets. For example, energy, test and measurement, general industrial. Among those, aerospace and defense is for us an important portion. And here we want to serve customers with reliable and best performing solutions. So reliability and ensuring the performance for the entire lifetime is what we stand for when designing our products. The value of the company is to deliver communication solutions for different markets. And here we bring concepts of mobility, safety, sustainability, and we want to translate those concepts into the value that our products offer to the customer. In the innovation field of aerospace, of course, we face different challenges. Among those, for example, what we see as a clear trend is the so-called swap, so size, weight, and power. We want to have, of course, the minimum weight. We want to have the reliable transmission, electrical transmission, but at the same time, also in this field, we are seeing some trends with cost reduction as well. So these elements have to be combined with the right placing of our products. And what we need to ensure every time, and is key for these applications, is to be sure that we have a reliable system, that once the system is set, it will ensure the right performance for the whole lifetime. A few words about trends and our products in the industry and in the market. We see a clear trend for internet access via satellites. This is something we have been working in the last years, and we have been working more and more in the future. And in particular, when it comes to GEO and LEO constellations, in general, the trends in this market is about a higher frequency. We have requests to go higher up to the V-band, and we have to ensure that our products are following these trends. When it comes to our portfolio, the answer that we can give in radio frequency is to offer RF cables and connectors, to offer assemblies that bring these elements together, and to offer as well radio frequency solutions when it comes to elements that put together the different components and ensure a full system. So this is another direction in which we are working, not only as a pure interconnectivity company. When it comes to space-specific solutions, we want to ensure the highest reliability. We want to have an outstanding electrical and mechanical performance, and ensure this is included in the system overall and the end to our customer. What are the requirements of the market for our products? Well, typically we talk here about satellite-based communications. It can be surface, airborne, or space-based radar communications. And we also see the application to connect high-resolution phased array antennas. As mentioned, the characteristics that we need to reach are having a higher frequency, microwave communication, going to bands in higher frequency, reaching sometimes even the 75 gigahertz. And the goals that we want to reach in this market is to have signal integrity, best RF performance, and of course having low weight and small footprint, because this is key for the systems that we are supporting. And there is an element that you describe here, and that will be part of the talk in the next slides, is the phase critical. It's clear that we have to ensure the reliability by having phase stable systems that do bring reliability in different environmental conditions. Why is phase stability a key in our systems? Well, we are talking about applications where there is a high throughput, where to reach higher frequencies, the speed rates are pretty high. And we also have systems, for example, where different pairs are used in order to eliminate noise. And when it comes to integrity and reliability, in this sense, the phase stability is a key element, and we need to ensure that in space, the phase stability remains consistent over the temperature. And this consistency, you will see later, is also part of the description of our offering and product family that relies on consistent performance over temperature. In this, sorry, not working. In this context, we offer coaxial cables, probably known in the industry by most of you, and I would like to put and say a few words around the electric insulation and the role that it has when it comes to performance of the cables. The typical material that is widely used since years is the PTFE, or Teflon, which is a reference for transmission because of its high performance. Why is it a reference? It's a reference because the dielectric constant is a key parameter to reach a high relative velocity and therefore sustain the high throughput. Now, PTFE is very good in this sense because of having a low dielectric constant, which ensure a high velocity, relative velocity, and it also has very nice mechanical properties that makes PTFE a good choice as a reference. However, and the reason, or the let's say the processing improvements that have been made over time to establish PTFE as a reference has to do with sintering and tape wrapping. Those are production technologies that have been used. Having an extrusion of PTFE without sintering allows to use powder, and therefore having also more air and lower density. This is helping to increase phase stability. Another way to help the increase in phase stability is tape wrapping. So having a tape of material wrapped around the dielectric, which also helps. However, it never brings the PTFE characteristics to the level that is necessary for the application. And the reason being, there is a critical limiting factor in this material. And this is not something that can be worked around through processing or different design, but it's an intrinsic material characteristic. It is what is normally called the Teflon knee. This is an expansion of the material that happens when the temperature changes, and in particular, it appears around 20 degrees C. This is, as you see on the graph on the left, the expansion as function of temperature reaches a high peak for the PTFE at around the 20 degrees C, which is not what happens with other polymers, for example, when it comes to FEP, where the trend is more consistent over temperature. The consequence of this is the phase stability and also the matching over that temperature. They are not guaranteed. If your system is exposed to different temperatures and the variation of temperature, then the cyanide integrity would be compromised and we would not obtain the reliability that we aim to achieve. We have worked since some time on alternative materials. The one that is mostly used is PFA. It's perfluoroalkane. And this material has also very nice characteristics, but the most important is the one to ensure a good phase stability over temperature. As you see in the graph on the right side, the relative phase change in parts per million, it's remaining quite constant for PFA, on the contrary of what PTFE is showing in temperatures ranging from 0 degrees C to 40 or 50 degrees C. It's not only about using PFA as a material, it's also ensuring that the processing of the material and the extrusion characteristics are defined at best to maximize the performance. And in particular, foaming of the material is critical. Why? Because by including some air into the dielectric and reducing its density, we can further increase the relative velocity and therefore ensure the highest throughput and fast transmission of the data. In this way, we can optimize the dielectric constant and reach levels of performance that are even higher. A few words about the importance of foaming for the dielectric. You see an enlargement, a zoom on a foam fluoropolymer dielectric as an example, as it is used on a coaxial cable, so that you can see how it appears in the microscope when it comes to foaming and when it comes to the reduction of density and presence of air in the material. Why is the dielectric characteristic so important? Well, when we are working in low frequency, most of the losses in coaxial cables are of the resistive type, and therefore they are linked to the construction of the cable, but they don't have a huge effect on the dielectric. On the other side, when it comes to the insulation, it is at high frequency that the importance is at the highest, and there is where the dielectric losses are the highest. So, and the reason being that there are intramolecular dipores which imply that there are losses in the signal, and therefore the fluoropolymers, because of its chemical characteristics, are one of the best choices. And in this condition, foaming of fluoropolymers is the preferred technology and preferred process that we use to injection of gas under high pressure, because in this way we have no residuals. And the technology in which we work on is to have the best process parameters to ensure the highest performance. The combination of these two elements is what leads us to the family of products that we have developed. So using PFA instead of PTFE, so a material that ensures the phase stability over temperature, and using foaming as a processing technology in order to achieve the best performances. What we have as a result of this development is the CT cable family. We call it consistent over temperature. It ensures to have the right characteristic in the environment of space, and it brings the characteristic of high stability, low attenuation losses, low weight, and perfect coverage. Few words on the results. What you see on the right side here is the phase stability over temperature, and here we compare an example of a cable with PTFE dielectric. It's the brown line, as a function of temperature compared to the 3 different cable dimensions that we achieve with this cable family. And you can see that in all these cases, independently from the diameter of the cable itself, the phase stability over temperature is very, very consistent in a large frequency range. This is really state-of-the-art, and this is really ranging from minus 50 degrees C to 125 degrees C. We don't get only stability, we get superior insertion loss performance, and we offer that with a flexible material which has easy to handle and easy to mount in different conditions. Below you can see some of these characteristics. As you see, through foaming we can reach a level of porosity between 30 and 60%, a low density, relative density of the dielectric, and the dielectric constant down to 1.4, 1.6, which is an excellent result and can bring us to a temperature service of 200 degrees and a frequency operation up to 67 gigahertz. Very high also for different applications that we have. What we would have liked to show is a demo kit to demonstrate how at low temperature the system is very stable. Unfortunately, we had not the demo kit available with us, but I can give you a flavor of it. I can describe it quickly, how we show the performance of our cables, and then I will come to a short video. This is for the multiplex 141 dimensions CT cable, so consistor over temperature, which is compared to a multiplex cable standard, which means that the dielectric is not PFA. On the other hand, the dielectric is PTFE in the standard configuration. You see in the picture a network analyzer, which is connected to the 2 different cables, the 2 blue cables that you see. One is the CT cable and one is the standard cable. And then we use, as you show in the picture, a spray that brings low temperature to below 50, to about minus 50 degrees C, and to show what is the comparison results between the 2 different cables. And here, if you can please let the video run on the slide, you see the 2 different cables. Can you please run the video? Here you see how they are mounted on the stand for relative comparison. In a second, you will see the application of the low temperature spray. So we reduce the temperature to well below 0 for both cables. And then afterwards, you will see the measurement of the phase. And as you can see, while on the CT cable, the consistent over temperature, the phase remains constant, the light blue line. In the case of the standard cable with PTFE, there is a drift in the phase, and we don't ensure the reliability that we would like to have for this product. Yeah, I think we can move to the next slide. A few conclusions to talk about today and beyond. What we have is the CT family, is what I have described until now, but I would like to give a few hints on the topics we are working on and what we want to achieve in our developments. Well, first of all, today, as mentioned, we have 3 different dimensions of the cable. We have a frequency range that is up to 33 gigahertz for the 141 dimension, and we have a very good level of insertion loss. And as you can see, we have different diameters and different connections possible for our cable assemblies. Our first work that we are doing is to improve the design of the smaller dimension to achieve the 40 gigahertz, because this is one of the requirements that we see in space applications. And we also work on a jacket that has improved solar radiation characteristics in order to ensure that the environment we are working on is handled in a pretty good way. We also ensure for our cable families that we don't only have the cables, we don't only have the connectors, we don't only have the ability to assemble the two together and to offer the complete system, but that we have in our offering the right portfolio, dimensions of the cables and characteristics of the connectors, shapes, venting holes when necessary, and all the different type of interfaces that might be necessary for the space. And the other topic that might come in the future is about the type of cables. What I've talked about is a flexible solution, because this is a more natural solution when it comes to reduce space or the need to adapt the shape and to work in limited space environments and to have a lighter and flexible material. However, we have in our portfolio, not with the same technologies, but already available some unflammable, semi-rigid, and pen-to-the-end versions, and we might also consider having different type of flexibility characteristics to be handled also for space application. This was a look on what we have today, how we handle these topics, and what we think to have for the future. I thank you very much for your attention, and for any question, I would be happy to answer to you.